Okay, good. So well, what kind of software are you using for solving these kind of equations?
They're not using software at all. They're manually solving the equations.
Manually solving the equations. Okay. So we're going to take one shortcut then. Okay, let me see. All right, so it works, but I'm going to be here in the corner. Okay, well, good afternoon, everyone. Sorry about that inconvenience of the room. I'm going to talk to Glenn to figure that out later on. And there seems to be an issue here with this. Probably. Is this working or not? But you see, it comes back.
Maybe if you put a sheet under it, it's like trying to focus on something.
I think it's broken. Okay? Okay, so guys, I think we're going to have to go the old way with the board. It's not working. All right, so we talked before about linear elasticity, and we solved single problems of linear elasticity, right? And today what we're going to do is to solve a general problem of linear elasticity. And when I mean a general problem, it's going to be very general. So and we're going to develop all the equations in order to get there. Actually, I think it's good today that we have the board, because we have to write a lot of equations. Okay. So let's get started. The general problem of continuum mechanics, you can solve it either analytically or numerically. We're going to see those solutions later, or some hybrids too. But first of all, we need to work with the equations, right? Let's say that we have, as we always do, and we always need a coordinate system, right-handed coordinate system, and for which, let's say that we want to solve a problem in which now inside a domain we have inside it a horizontal wellbore, and further we have here fractures around it. Let's say one small one, one big one, and we want to know what is the state of stress in a particular region in this rock, and also in 3 dimensions. So how do you solve that? How do you go on solving that problem? And it's in an arbitrary location with some arbitrary boundary conditions, and you have to solve this. Okay, so this would be kind of a general problem, but an applied problem. I could also do something very general, and this is a very famous potato problem, because this is like a potato, just a general continuum, which it may be constrained to not to move in some direction at some point, or in a given surface, may have some stresses, and in another point you might have forces, and it has a volume, and also here it has a surface, and perpendicular to a surface we have a normal vector n. But it is something very general. I'm missing something. What am I missing? Probably we could add here some body force B. Could be gravity, Could be magnetism. If you have problems or you're going to solve some production, it may be drag force. Could be anything related to the body of the solid that we're going to solve. So the first thing that we're going to do is we're going to write the stiffness matrix in a more convenient form to what we have used before. Okay? So let's write the stiffness matrix over here. And the stiffness matrix is going to allow me to calculate stresses as a function of strains, right? 1, 3, sigma 1, 2. So I do not remember this on my heart, guys, and I'm far from my notes, so you're going to have to help me, okay? So here I know that we have Young modulus, and if I remember correctly, here we have 1 minus or 2, I don't remember. Just help, can you help me, guys, with this one? So numerator.
Okay, it's E over 1 plus nu times 1 minus 2.
1 plus nu.
1 minus 1.
Okay, and nothing here, right?
Yeah,
Okay. All right. So, and this one is going to be multiplied. This one I remember. This is nu, 1 minus nu, 1 minus nu, nu, 1 minus nu. It's okay?
I have
The opposite. Okay, I didn't remember well then. So, 1 minus nu and 1 minus nu. And here, these are zeros, these are zeros, and here I need to get a G.
1 minus 2 nu over 2.
1 minus 2 nu over 2. Okay. So 0, 0, 1 minus 2 nu over 2. So you already had this before. And let me finish here with the strain tensor. Epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, 2 times epsilon 2, 3, 2 times epsilon 1, 3, and 2 times epsilon 1, 2, right? Okay. So what we're going to do now is we're going to change this stiffness matrix using some other moduli that are going to be more convenient to solve these equations. And these moduli are the Lamé parameters. And notice that this coefficient over here, I can write it as 1 minus 2 times Poisson ratio plus Poisson ratio. It's the same thing, right? So I'm going to take advantage of that, and with the following definitions of the first Lamé parameter and the second Lamé parameter, I'm going to be able to write this stiffness matrix a little bit differently. And that definition is going to be 1 minus 2 times nu E divided 1 plus Poisson ratio 1 minus 2 times Poisson ratio. And notice that it's this guy times that part of that number, and the shear modulus is going to be equal. The second Lamé parameter is just the shear modulus, is the same, and that one is going to be equal to E multiply just this one times that one, so it's going to be equal to 1 plus Poisson ratio. These are what are called the Lamé parameters. Okay? So what we're going to do now is we're going to replace those parameters in here in order to write that stiffness matrix again. And if we do that, notice that here we have this component is there, is lambda, right? And we're going to have an additional Poisson ratio, and that's going to allow us to also put the shear modulus. Let me see, I always forget a little bit how to do this part. So I chose the wrong part of the Lamé coefficient. It wasn't the first part, it's the second part. Is that one. And notice that when we combine these two, so that part of this multiplication is just going to be the Lamé parameter. And this other part of the multiplication is going to cancel out with this one. So this one divided by that one is going to be 1. And then we're going to be left with this one 2 times, right? So I'm going to be able to write this again as nothing here, and now this is going to be lambda plus 2 times mu. And notice that here now we have this lambda, just the Poisson ratio of the number that I had before. So just going to be lambdas and lambda plus 2 shear modulus. And this one, when I multiply what I had before times what I have over there, I'm just going to end up with the mu. So this is a much easier way to write the stiffness matrix than what we had before. And because it's much easier, that's what we're going to use in order to solve our equations. Can you remind me what are the equations that we need to solve a continuum mechanics problem? There were 3 types of equations, and we're going to write them again here. Okay, so balance of Cauchy equation, that's basically equilibrium, right? So here we have the divergence of sigma plus any body forces, and if I don't have any acceleration, that's going to be equal to 0. That's equilibrium. Then we need kinematic equations. Kinematic equations link strains to displacements. And if I assume now, I'm doing an assumption now, okay, that it's needed to write this. If I assume small strains, this is going to be 1/2 of the gradient of the displacement vector plus the gradient of the transpose of the displacement vector. Basically, it's going to be the gradients of displacement, but in this case it's transpose. And what that transpose thing does is to take the average when we had those terms in the off-diagonal terms. You remember in those off-diagonal terms we had an average of, for example, du1 dx2 plus du2 dx1. That's what we're doing here. So here, remember that we're assuming small strains. And there is one more that we have used a lot so far, and we have worked a lot so far on, that are the constitutive equations that are going to tell me that sigma is a function of the strains, and in this case I assume linear elasticity with constant coefficients. And in our case also we're assuming an isotropic solid. So usually this one I call it the linear elastic isotropic solid. So we have all the equations to solve our problem, okay? And before we go on solving this general problem, I'd like to make an analogy with another set of equations that probably many of you, particularly the ones in petroleum engineering, are more familiar with, which is the fluid flow equation. For solving a problem of fluid flow, you have a very similar set of equations. So here, this is mechanics, and here, let's say, this is fluid flow. What is the first equation that you need in order to solve a fluid flow problem? Material balance, right? Or mass conservation. And what is the equation for that? Of Q equal to 0. Basically, that equation tells you that the variation of Q's or of flows, of flow rates, it has to be the same, or it doesn't have to change as you get into a solid. Let me explain this here with a cartoon. If you have a Q1, which is 2, and then you get 1, that means in another direction, if you're getting 1, in this direction you must get 2. But everything that comes into a solid, 2 plus 1, 3, 2 plus 1 is 3, has to be the same. That's continuity. So this one also you can write it as dq1 dx1 plus dq2 partial x2 plus, what did I write? Z3 dx3. It's a divergence because it's a scalar. You add everything, and that has to be equal to 0. We're going to see now a gradient. A gradient is going to be of a scalar field. It's going to be a vector. So, but it's the same thing. You see, it's the divergence of Q, divergence of sigma, and conservation of mass, conservation of momentum. Similar equations. What is the second equation that you need in order to solve a fluid flow problem? We're getting there, right? But I need one more equation in order to tell how fast the fluid is going to go. Which one, Min? Which one? It's not really a kinematic equation in this case, but it's going to be a relationship between Q and P, which is where P is pressure. It's going to be Darcy equation, right? So Darcy equation tells me that the fluid flow rate is going to be K divided by the viscosity times the gradient of pressure. So this gradient of pressure is a vector, right? And you multiply that times scalar, it gives you a vector. Uh, um, you could, I don't think you could really call that it's a sort of a constitutive equation, but not that much. In order to get here, and we're not going to do this, that's where you need a constitutive equation, which is you have to assume laminar flow, right? And you have to say that the shear between two parallel planes of flow is going to be equal to, or is going to be proportional to viscosity times shear strain rate. And with that would be sort of a constitutive equation, but you can get to this other equation later on that is the Darcy equation. But notice that here it's analogous to the kinematic equation in the sense that there is a gradient of pressure, and here we have a gradient of displacements. So it's very similar, and the problem that we're going to solve is going to be analogous to that one. Now, basically, what do you do in order to solve this equation now? If I wanted to solve this equation, I'm just going to write what Q is over here, right? So the divergence of Q, let me save some steps over here. I know what Q is over there. dx1 and Q1 is going to be minus K viscosity dP dx1, right? And this is going to be partial dx2 minus K mu and so on for the three terms. And eventually, you're going to end up with an equation, and we assume that we take this one out because we assume that it is constant. It's going to be second derivative of P respect to x1 2 times plus second derivative of P respect to 2 times second derivative of P respect to 3 2 times, all of that equal to 0. And you guys know this equation, right? So that's the Laplacian of P. And if you solve the Laplace equation, then you can solve P. Once you know what P is, you can solve for Q. And that's the end of that problem, if we are not considering time. So we're going to have to do the same now with the mechanical equations, okay? And in order to do that, we're going to have to expand this term and put what we have over there. So let's go through that. Any questions so far? No? This takes a lot more work than writing on the paper. I have forgotten how to do this. All right, so let's solve these equations all together. Tell me the first equation, the first line of the equilibrium equation. I'm ready to write. What is that going to be? I'm going to help you. Sigma. That's the first line of the equilibrium equation, right? There are three equations. in what we have written so far. Okay? So we'll solve just one of those equations first. So let's call this one number 1. Okay? But now, I like that you tell me what is sigma 1, 1, sigma 1, 2, and sigma 1, 3 as a function of the Lamé parameters that we just calculated. So I'm going to replace sigma 1, 1 now. And what do you get? What is sigma 1, 1? Okay, so lambda plus 2 mu, and in the off-diagonal terms, we just have lambda, right? So look what I'm going to do. I'm going to write epsilon 1, 1, epsilon 2, 2, epsilon 3, 3 times lambda plus epsilon 1, 1 times mu. 2 mu, right? That's sigma 1, 1. Let's write sigma 1, 2. Sigma 1, 2 is going to be just mu times 2 times epsilon 1, 2, right? And 1, 3 is going to be mu times epsilon 2 times epsilon 1, 3 plus F1 equal to 0. Okay, so now we have used the constitutive equations with the equilibrium equations to write all of that as a function of strains. But now we know that we can go one step further. And we can write now these equations as a function of displacements, right? And we know those equations too. So this is going to be, what is epsilon 1, 1? That's an easy one, epsilon 1, 1. du1 dx1, right? Plus du2 dx2 du3 dx3, and all of that times lambda plus du1 dx1 times 2 times that. So this is that term. Let me change it for brackets. Plus this is mu, this is 2 times, and now I have 1/2 of du1 dx2 plus du2 dx1, right? Just let me know if you see any mistake. Plus this one, you saw a mistake, to 1/2 du1 dx3 du3 dx1 plus, I told you we were getting into long equations, so there you go. So these two cancels out. I don't worry about that anymore. All right? Okay, so now is when we have to do some smart reaggregation of terms and try to recognize which ones over there are we can group together. So let's apply here distributive property. I'm going to take this lambda, since that lambda is going to be a constant. I'm going to take that lambda out, and it's going to be lambda times ddx1 By the way, guys, what is this? Volumetric strain, very well. That's volumetric strain. And so this one was the part with the lambda, right? So now I'm going to write the other part with the mu. Notice that I have x1 here, and I have x1 over there. So this is going to be 2 times mu second derivative of u1 respect to x1, right? And let's continue. I go with this one. Again, I'm going to take the shear modulus here to the front, and here I'm going to have a second derivative of u1, but now respect to x2, and here I'm going to have a cross derivative of du2 dx2 dx1, and the other one is going to be we're not too far, guys. We're 70% done, okay? So don't worry, this is not going to take too long. But it's important to do it at least once. If you don't do it here, I don't think you're going to do it anywhere else. So we just do it once, go through the pain once, and then you know where that equation comes from. All right. So I have just expanded all those terms. Where is the red marker? Okay. So here is where I'm going to start grouping some terms. And the first one that I'm going to group, or I'm going to simplify, is going to be the first term that we see over there. So I'm just going to write it. Can you guys see here on the bottom, or I should write somewhere else? It's okay? Probably, well, we'll see later with the camera. I don't think you can see anything with the camera, but I'll pass you my notes on this later on, okay? All right, so